Hey, I'm glad to be here, and as Michael said, this will be an interdisciplinary talk, maybe sort of like a fusion cuisine of education and psychology and computer science. I want to talk about big data and discovering tacit implicit knowledge and using that to improve learning. And my overall argument is here on this slide. I want to first try to convince you that we are not aware of most of what we know and learn. And as a consequence, the typical approach for designing instruction, whether that's writing a textbook or authoring lectures, is fundamentally flawed by a basic lack of information. That self-reflection that we use to design in lectures and textbooks and so forth is drawing on too little information. So instead, we should be basing instruction not just on our intuition, we shouldn't give that up, but also being informed by data and by the science of learning. And I'll illustrate for you some approaches we've taken to draw upon data to tap into what we as experts or what students trying to acquire expertise know and learn, and as well as examples of using computational modeling to dig into those issues. Importantly, we want to then demonstrate that those insights really work by redesigning courses based on them and comparing them in experiments to show you that you get improvement. So that's the closed loop part. I'm going to start with a little background, then give some examples of these data-driven models, and give you a brief sense of this computational theory that we're developing of student learning in these areas. So going back to some of the early foundational work, this is sort of a CMU take on early AI and cognitive science history, but it's one that's relevant to sort of my core way of thinking. So Newell and Simon did this work on human problem solving way back in the early 70s, and they used this technique called think aloud, where they had experts think aloud as they solved problems, and that was their primary data source for tapping into the nature of expertise. And that work led to things that came later. I mean, they built the first chess-playing computer, but of course we see today how powerful those technologies have evolved to be. But they also had insights into the nature of expertise, including the notion that experts acquire something like 10,000 chunks of knowledge to become an expert. That's probably already an indicator that it's maybe hard to reflect on what one knows if the volume is that high. But another thing that was very compelling about some of the work they did, for example, in chess, was this notion of perceptual chunks, and it is best illustrated by this task of giving a master chess player a board position in the middle of the game. Say there's 28 pieces on the board. 5-second exposure, sweep it away, ask the player to reproduce that board, and they can do that very accurately and quickly. Novices can't do that, and interestingly, experts with those same 28 pieces randomly placed on the board can't do it either. So they've learned particular patterns of pieces, just like you learn patterns of letters that form words, and you can quickly remember what those letters are when they form words. So too do chess players learn these patterns. And it's not like they're trying to do that, they're trying to play chess, right? But it turns out that their brains acquire these patterns, and it might actually even be functional, but they don't realize that they're doing it. Herb Simon and others did some later work in developing not only models of doing complex tasks, but adaptive systems that could acquire knowledge of doing those tasks. So this was early symbolic machine learning. Adaptive production systems was a key approach. Actually, one of the really, I think, interesting papers in this is sort of little known proceedings of the National Academy of Sciences paper that Simon was involved with. And this, among other papers, really made a big emphasis on the hard part of becoming an expert is learning essentially the retrieval cues or if part of our knowledge. We often can articulate what we do in an expert area. Those are the actions in the then part, but when and why we do them is the hardest part of learning, and also probably the most tacit of what we learn. They did some demonstrations actually of using this to guide better instruction in math and physics. There was also work developing cognitive architectures like ACT-R and SOAR, and some of that led to intelligent tutoring systems, like early work on a programming tutor teaching the Lisp programming tutor had an impressive demonstration of teaching programming in about 1/3 the time it takes to learn programming in a typical situation. One of the key ideas in ACT-R helps to highlight this tacit knowledge thing. And it's not simply, I guess in philosophical terms, these distinctions between declarative and procedural might tempt you to think that's declarative is what you can say and procedural is not. But ACT-R cuts it a little bit differently. There are declarative elements like the structure of the perceived world that are not necessarily easy to verbalize. Things like the first language grammar, you know, your natural language, that grammar, you don't learn that explicitly. You'd have trouble explaining, for instance, why you use the in some places in a noun phrase and not in the other. You pick that up like the chess master through experience and through exposure. These perceptual chunks are really powerful in expanding experts' memory, organizing their intuitive reasoning, allowing them, in essence, to make leaps of inference by seeing the world in bigger chunks. On the procedural side, these cues help, for instance, surgeons make choices in surgery, academics plan proofs, social design decisions, get at the conditions and logic behind decisions and planning. If we ask how much of our knowledge is each of these, there are some empirical investigations that suggest these things we can't articulate, this tacit knowledge, is about 70% of what we know. The remaining 30% that we can directly articulate is actually quite small. And I'll say a little bit more about that, but if you want to ask me later, you can probe a little bit about how those numbers came about. Prefacing this simulated student theory I'll get to later, wanted to put on the table a few of the claims that that are part of that theory. So following this tradition, the notion that much of our learning comes from inducing from experience, from examples and by doing, and that kind of learning is mostly outside of our conscious awareness. That kind of a learning involves challenges for our brains corresponding to the things I was emphasizing earlier, learning cues for decisions, or the if part of the production, and learning the deep representational structure of a domain from perceptual input. And the computational modeling framework we have mechanisms to perform these two challenges. And part of this approach is to suggest that, you know, what we actually spend a lot of our conscious time in learning and instruction, verbal forms of instruction, is somewhat secondary in the process. And so I think there's, you know, something challenging there in the sense that it's in our conscious awareness, so it feels more primary. But in fact, if you look deeply into how learning works, it guides us, but doesn't really get us there. So visually, here's the dilemma. Experts, if you believe this notion, can describe only 30% of what they know. The rest, we don't know what we know, so instruction based on intuitive design lacks information and thus is likely to be somewhat flawed. Here's a piece of that evidence from a study that involved interviewing experts in a surgery procedure, catheter insertion. And this is recording for different surgeons how many of the steps in the final procedure that they came up with through these multiple interviews and probing and some rational extension of what the procedures needed to be. How many did they what proportion did they originally mention? And this 30% comes from essentially that the decision steps are a minority of what they're mentioning. So this thing I'm illustrating here is a form of cognitive task analysis. There are a number of ways to do it. Think alouds that Newell and Simon did are one of those ways. Clark and colleagues have done this structured interview form. One thing that's really powerful about what they've done from an education perspective is they've taken the insights and redesigned instruction and then compared that instruction to existing instruction. So in this surgery domain, the control condition in these studies was teaching that these surgeons in med schools have developed before. So these are really smart people, right? They're developing a really high quality course, but they're doing it largely based on their intuition. When they did these think-alouds, they discovered subtleties of the surgery procedure, like even the way in which the person's holding the needle here, that weren't being articulated in the course, in the original course. And when they modified the course based on these kinds of insights, they got much better outcomes. And they interestingly not only tracked those outcomes through doing the typical kind of paper-based post-test in which the surgeons who were in the treatment condition did better. They also looked at their performance in the field, and they were much better at the surgical procedures, as demonstrated, for instance, they had many fewer extra insertions of the needle. So very practical, important, and powerful outcome. There have been not a ton of these kinds of studies. You can imagine they're kind of expensive to do, both this intensive interviewing process as well as the redesign and the experiment. But about 6 or so in a small meta-analysis really showed a quite substantial effect across these studies of this kind of approach. So one of the things I've been interested in over the years is, can we find ways to build upon this extremely informative approach, but find methods that get beyond some of the issues of subjectivity and time cost that these methods incur, and take a more quantitative approach that uses data, and does so by asking 2 key questions. One form of data is to look at the difference in difficulty of related tasks. And by seeing those difficulties, we can infer through the difference what cognitive processes might account for those empirical differences in difficulty. And the second is looking at task performance over time to see practice, learning by doing in some tasks may transfer to others, but not to another category. And again, we can use that to make inferences about the underlying malleable cognitive processes, the components that make our intelligence plastic and changeable. So to give an example of that in a more academic domain, in early work that we did developing an algebra course and an intelligent tutor for algebra, I was interested in what I was hearing from working with teachers, and I guess to some extent it felt like my own experience, that story problems in algebra were difficult. So here's this kind of contrast between tasks where we've tightly controlled features of this task. So as you may have observed, these are all the same mathematics. All 3 of these problems have the same answer. The only thing we're varying is the context of the presentation. This is an equation. The top has a story. The middle's in English, but without the story. And question is, which is most difficult for students? And can we get a sense of what process students are using to solve these problems? So what do you guys think? I'll show you data from, it was about April in a 9th grade algebra class in Pittsburgh. So they've had, maybe 7 or so months of experience with algebra in a high school algebra class. Who thinks the story problem? You have a hypothesis?
I was going to say it seemed like the equations would be the hardest.
Why is that?
I think stories are natural structures that people understand, and probably empathize with, the student can empathize with maybe Ted, and will find it more interesting to solve the problem.
So that would make the first one easier.
Yeah.
What about the second one?
Well, the second one is closer to at least a story, but still it's not as emotional as the first one.
Yeah, well, there's no story there, right? Yeah, other thoughts?
So you said it's high school students, right?
Yes.
Then I guess it's the equation is the easier for them. And then it's the story problem. And then I think the word problem is probably the most difficult for them.
Yeah. So how many say story?
That's what easiest.
Hardest. Sorry, hardest. How many say word? How many say equation? Come on, stick with it. Yeah, I was actually designing this thinking I could get some insight into how story problems are solved, translated into equations. This might be a sort of intermediate form, and I could unpack that. You guys are mostly consistent with what math educators believe. And unfortunately, most of us are wrong. What the data showed is that you were right. Maybe not for the right reason, but yeah, the big difference is actually between the equation and the word problem. So it's not about the situation. It's actually a small effect of the situation on decimal arithmetic operations. We never see students subtracting $66 from 90 cents in the top problem, but they do in this problem sometimes subtract 66 from the 90. So that's essentially accounts for the difference between 70 and 61%. But the big difference is between the problems expressed in English and the one expressed in the language of algebra. Yeah?
But in some way, in the word problem, aren't you really giving them instructions as to what to do? Because you say, if I multiply it by 6 and then add 66, I get it. So to me, that almost seems like instructions as to what you should be doing.
Yeah. We've replicated this number of times, and one of the things we've manipulated is whether the operators are made explicit or whether they're implicit. And a more natural way of saying it, they'd be implicit. But that makes almost no difference. It's about 70% correct when they're implicit. There's some slight effects on strategies in that case, but no big difference in difficulty. Yeah?
Does the relative difficulty of the problem also depend on the proficiency of an individual student? So a math.
We replicated these kinds of problems with CMU undergrads at one point, and you'll be not surprised to hear that the bars shoot up like to 98%, but that one only goes up to 94. So it actually replicates with mean SATs of like 690 or something like that. Yeah. But the other thing we did is we manipulated the difficulty of the problem. So one feature of difficulty that flip-flops this relationship is if the story or equation refer to the unknown twice. So x minus 0.2x equals 38, or Ted bought a coat at a 20% discount and he paid $38. How much was the original price? There, the story problem's harder than the equation, and it's because there they need the equation to solve it. Here they're actually able to solve these problems without using the equation. But what's the most interesting thing about this is why this is hard and why we don't experience it as being hard. And what our analysis suggested is basically it's kind of a linguistic phenomena. There's a language of algebra that your brain and its ability to learn language without language, that's how you learned your first language, is still soaking up the grammatical patterns and so forth. It needs to, because you don't naturally know how to read this. You don't know how to chunk the phrase structure that you should do multiplication before addition. You can be told that, but that doesn't mean you're going to, in the moment, do it. The patterns of errors we saw, and in fact, the tight contrast between these two suggests that the real difference is essentially not being able to read this reliably. Just like, imagine you were in your first year of a Greek class, right? And after 9 months, you were asked to say what this means versus say what that means. It'd be easier to do in English than it would be in Greek. Yeah?
You get the same kind of results when you test this on students from different countries?
We actually replicated this in Russia because a colleague of mine was saying they start using the algebraic language in second grade, problems like x plus 2 equals 5. And as a matter of fact, they actually didn't flip-flop, but they're roughly equivalent. They've had 7 years of experience by 9th grade with the algebra language, so they're actually able to comprehend it better. Yeah?
Is this the exact format of the equation that you gave the subject?
In this study it was. We had others where we used 6x, and that actually doesn't matter. We actually had studies where we did a line instead of an x and a box. Those are slightly easier, with the line being slightly easier than the box, if you can believe that. I never believed it would be possible, but somebody hypothesized that it would be. But somehow fill in the blank is more natural than small effects. But is that what you were getting at, the 6x? Yeah. Yeah, it turns out, we thought that might be harder, but it turns out some students don't know what the asterisk means. So there's a lexical issue here, and 6x is, again, a grammatical issue, right? That's a particular grammatical form that juxtaposition means multiplication. And just because I tell you it once, just like I could tell you in Russia how to conjugate a verb, doesn't mean you can do it, right?
In math educators say, is there a distinction between what more experienced math educators say versus ones that are less experienced?
Well, it's interesting you asked that. We did do surveys of teachers, and in one of those surveys we had elementary, middle school, and algebra teachers, and the algebra teachers were the worst at this prediction task. They were the ones who, like many of us, including me, want to say, yeah, the equations are easy, right? Because they're easy for them. So yeah, we started to use this phrase, expert blind spot. The more expert you become in something, the less reliable you are at predicting how hard it might be for somebody to use, especially if that expertise is rather tacitly acquired and you don't have much conscious awareness of it. Was I getting at the nature of your question?
I think that's very interesting. I mean,
Yeah.
So sometimes teachers are, like there's somebody who's like, or people will think is a really great teacher.
Right.
This teacher really did more for me than other teachers that I've had. And I'm wondering if they're getting at something different from what other teachers are. How that dynamic relates to what you're saying.
Yeah, well, I think it depends on what you mean. Certainly people's judgments of teaching can go to like
It could be many things.
personality and yeah.
Things there, but I'm wondering if there's.
But I think ultimately, to the extent that that teacher is being perceived as effective because they're able to select tasks that make the subtle distinctions that let me understand something that wasn't obvious to me, that other professors would have thought it was obvious, that would be consistent with this theory. In other words, if I'm sort of more aware of distinctions that make the if part different, even though the then part's the same, you need to learn it two different ways, and I give you both of those examples, I'm probably going to be a better instructor than the one who just gives you the one example and expects you to be able to induce and generalize to the other context. Yeah.
So, well, one reason why the teachers may be bad at estimating is because they have become experts and they have forgotten how it is to be a novice, which is this blind spot theory. But it could also be that they're used to teaching, and maybe teaching makes them better at symbolic manipulation. And so, it simply may be that they've taught students, which is why.
Yeah, well, there is the issue that they may be self-reflecting on their own ability, and it's easier for them. There's the issue that maybe it was harder, but they forgot. And then the other one, which I mostly believe, is they never realized that they were learning it. Because most of that learning, like first language learning, was happening tacitly and implicitly. Yeah?
Sorry, I still have a question about what do you mean by the linguistic phenomena, by the equation, because
Can we come back to that? Because that'll be, when I talk about our simulated student and how we use grammar induction to learn algebra, it'll make the language analogy more powerful. Yeah, spent more time on that than maybe I planned, but I think it's worthwhile. Here's a screenshot from the middle of the Algebra Cognitive Tutor that we developed. There's a lot of activities like this. Some are more like practicing your serve or your backhand. They're more isolated. This one's a bigger task, like playing the whole game of tennis. So in these bigger tasks, students are analyzing some intendedly authentic problem situation, like comparing two different cell phone plans, and they're using multiple representations, not just equations, they're not shown, but that's part of it, tables and graphs, and developing a model of the problem situation and using that model to answer questions. And as they're filling in this table, or drawing the graph or solving equations, the tutor is following them along, able to assess every step in the process, and if necessary, give feedback when errors are made, like here the student forgot the fixed cost of that of the current plan. But also students can, when they're challenged with hard questions and aren't able to figure out how to go about finding out when the two plans intersect, they can go up here and click the hint button and get help. So 2 forms of instruction here: feedback on errors or next step hints for what to do next. And if the student is able to figure out from this higher level hint, they can ask for a next one. And eventually it grounds out in giving them an example, not of the whole solution, but of just the next step. And then it's back into the student's hands to learn by doing. So an instruction comes only when needed, not when I think you need to hear it, but when you demonstrate that you need instruction because you've made an error. And it starts with verbal instruction, which actually the data suggests maybe not all that valuable. It ends with an example of what you should do, and that actually seems like that's probably the most powerful. If you don't know, the best thing may be to just, instead of being told, to be given an example, and then you can induce from that and given a later chance to learn it. With respect to giving a later chance to learn it, if you're making errors, we're tracking what skills you're having difficulty with, and then assigning new activities based on this skill profile so that better students can skip past stuff fast. Students that need more help get more help in the areas they need it. And the way that's made possible, the fundamental piece of intelligence in this system, is the cognitive model, a system that can solve the problems in the domain in various ways that students can. Here's just an example of that in the algebra domain, 2 different strategies represented as if-then rules here for dealing with a problem like that one. Either of these are correct, and here's a common error. If you have a model like this, and the crucial thing is to get these right. This is a kind of a made-up example, but I give you examples later of how getting this right can be subtle. But all the instruction that the tutor can deliver is based on this model. It will give context-sensitive instruction depending on the structure of the model, as I illustrated earlier, and it's also going to update the model of what the student knows. There's a Bayesian estimation scheme here underlying it to select upcoming activities and determine the pacing. So those skill bars are based on, for each student, there's an estimate of the probability that they know each skill, and that can be then used to select what kinds of learning by doing activities would help them the most. Been lots of large-scale field trials of this. It's also been very widely disseminated. About 600,000 students per year are using these courses about 2 days a week. And those numbers, those are not just starting numbers, those are finishing numbers. Those are students getting through these courses at it's about almost 3,000 schools are using it across the country. The field trials have been going on since the earliest quasi-experiment we did is reflected in the graph here. In particular, this represents one of the results we often saw is that if we design assessments to get at some of our key goals, like authentic problem solving and being able to use multiple representations to represent functions, we get huge results. We get smaller but statistically reliable results on standardized test questions. Many studies in between, but one of the most recent is actually the largest yet. This was about 140 or 50 schools where classes in those schools were randomly assigned either to use the Cognitive Tutor Algebra course. By the way, it's a full course. We developed the text, teacher professional development, and the software. Where they're either randomly assigned to that or to use their regular algebra course. And the effects here are particularly strong in the second year of implementation, and the somewhat oversimplified result of a very complicated analysis is that students in the Cognitive Tutor course over the school year learned about twice as much as students in the traditional algebra course. Very rigorous, large-scale field trial. These field trials have certain kinds of weirdnesses to it, that if students are assigned to the condition, they're treated as though they got it, even if they didn't. We've seen in some of these implementations, some of the schools intend to have students use this curriculum, but don't actually use it. And these policy level studies require that you count those students as having used it. Certainly interesting issues there about methodology. But the real point I wanted to make about these is while these are some pretty good results, there's certainly plenty of room for improvement, both in terms of the practical outcomes, but also scientifically. We made so many decisions in building these courses driven by our own intuitions, having insufficient data or insufficient science to guide those decisions. So we created this LearnLab Center about 9 years ago with generous funds from the National Science Foundation around the idea that we could use these widely disseminated technologies as a way to do research. So these include not just our math cognitive tutors that are used in mostly middle schools and high schools, but a number of online courses, mostly at the college level, developed at CMU through the online learning initiative that Candace Till was directing, who's now here at Stanford. Also work in language learning domains, and in a number of data sets using educational games. So the key idea here is kind of like, Googleizing education, if you will. By having these technologies out in the field, we can embed studies in them, we can collect the raw data, and we can build our better theory through the technologies as kind of a deeper instrumentation of what's happening in the learning process. So the social part of this infrastructure was facilitating researchers. Some of these are laboratory psychologists who wanted to get out into the real world, help them run studies in schools by organizing that process for them. And part of that organization is technical in that we'd help psychologists implement studies in these technologies. So we have, through this process, and actually increasingly just through people adding to our data repository, we now have, I think it's the world's largest open repository of educational technology data. It's about 500 data sets from a wide variety of domains. But we've also ran many of these in vivo experiments, or they use the language of industry, these A/B tests, where instead of that study that I showed you, we're manipulating all kinds of things, right? That course is different, not just because of the technology. The text is different. The teacher professional development is different. In these studies, they're tighter principal testing studies where we're varying one thing. They might last for maybe a couple weeks or even a day session with a pre-test and a post-test between them. And so done over 300 of those. This graph represents a subset of the content areas that we're focused on in those studies. So some language learning things, some math and science things. And on the other axis here are the things that were manipulated, like the treatment condition had an optimal scheduling of practice algorithm and the control condition didn't. And we used this experience to put together a framework, essentially making some dichotomies or taxonomies of different kinds of knowledge, different kinds of instruction, and different kinds of underlying learning processes that are facilitated by those different kinds of instruction. So the taxonomy makes very finer grained distinctions, but at a sort of higher level here, between facts that are like constant to constant mappings, like an English word to a Chinese word, rules or skills, which are mostly tacit mappings of variable situations into dependent variable responses, and then articulated verbal knowledge of principles. Increasing in complexity here, both complexity in the sense of you could look at description length that get longer to describe, but also complexity in the sense that if we look at the time to execute the corresponding operations, the time gets longer. And then we also have this dimension of different kinds of instructional manipulations that may be associated with learning processes to facilitate memory, or to facilitate induction, or to facilitate understanding. And again, these get increasingly complex too, as sort of characterized both theoretically and temporally. These books, by the way, are some sources for many studies that, various paradigms of research in educational and cognitive psychology explored a lot of these dimensions and been published in a lot of these resources. But we were trying to put some organization to that. What's in this content of this table is some examples of particular studies. So here, for instance, this shows 3 different domains we manipulated, adding worked examples to our tutors. And the outcome was positive for the treatment. Here are a couple of studies where we had students explain their steps, in some cases in contrast to getting explanations from an instructor, or in contrast to not having to explain. Interestingly, in some domains, we saw no effect of this self-explanation manipulation. And there's a temptation in this graph and a theoretical reason to believe that maybe there's an association here, that the complexity of your knowledge goals should be matched with the complexity of the kind of instructional intervention that you focus on. And that complex forms of instruction, like having a classroom dialogue, may not be very effective for learning Chinese vocabulary, for instance. So, and that one's rather intuitive, but it gets more subtle in some of these cases, where prompting students to self-explain why they chose a particular English article actually enhances learning, but it takes more time relative to not doing it without getting any more positive gain. And the fundamental theoretical idea here is it's because that most of that activity is not enhancing memory. It's targeted at enhancing understanding, but memory is the primary learning process for acquiring vocabulary. I could give a whole talk about that upper corner, and we have a recent book chapter that talks about that. But not only has a lot of our work been more in the middle here, but I think this is really sort of fundamental, and it's somehow underemphasized. Cognitive psychology loves to do studies about memory, and because we're consciously aware of the verbal stuff at the top, that's what we mostly think about when we think about instruction, how we're communicating to each other in lectures. And the middle part often gets left out because it's happening tacitly. So that's where we've been doing most of our exploration. I think, just to give a kind of sense of a status of where we are, we learned as much in this center about what we don't know as we learned about what we do know. And I think we know a lot. I would characterize it in a metaphor with transportation. It's like we have Model T cars now. It's much better than walking or having a horse-drawn carriage, right? But what we could have in education is jet airplanes. What it will take to get there is sort of analogous. It's going to take a lot of work. It's going to take a lot of advances in the science and engineering, not of jet engines or how planes work, but in deeply understanding how learning works and how we can use technology to make it easier and faster and better. So the part of that development of understanding goes to thinking more deeply about what are the best forms of instruction. And we often get caught up in debates about instruction as if there were just 2 ways to teach. You've probably heard about the math wars or the reading wars. Like, the reading wars are phonics versus whole word. There's just 2 different ways to teach. Or math is like back to the basics or understanding. They tend to have this kind of give students more assistance versus more challenge character to them. Academics kind of make a lot of these binary distinctions too, just a lot more of them. Here are some examples, and the bold italics is an indication of where the literature seems to lean on a lot of these issues. Although, and some of them, there's work in both directions, and some of these you'd find people disagreeing on the status of them. And some of them, which are apparently different in that there are different paradigms of work and different people involved. If you examine them closely, these 2 things are essentially the same dimension of manipulation, but one paradigm's coming out with a different answer than the other. And it turns out, I think, this is one of the things that inspired that knowledge instruction dependency, is that most of these studies are about facts in memorizing facts, and their practice is much more important than study. Whereas most of these studies were about skills, and their studying examples is doing that much more than we usually do, say, in a math and science class. You know, we get homework assignments where you get problems to solve. It might be 10 problems to solve. What this literature says is that you learn more if half of the problems were solved for you, and you study those half of those problems and solve the other half. That gives you more information to induce the patterns that you need to learn. And of course, we always give examples, but the problem is instead of giving 5 examples, and the lecture usually only has 1 or 2, and then some of the subtleties that you need to learn aren't represented in those examples. So you have no information on which to base them. Extending this idea out a little bit, I started to think about how many different instructional options there really are, and the fact that these binary distinctions already hide some of the subtlety in the sense that you can take a distinction of like massed or focused practice versus distributed practice and come up with a number of intermediate solutions, like gradually widen the time between practice intervals. And you can combine these dimensions together. So here we can take the dimension of study versus test and combine it with the other. And now we're not at 2, we're at 9. But that's only 2 of the dimensions, right? Should the examples be concrete or abstract or some mixture? Should the feedback be immediate or delayed? Should I block topics or interleave them? Should the instructor be doing the explaining or the student doing the explaining? And you can again combine these with, for the most part, there's some exceptions, but for the most part, all these can be combined with others. And there are many more such dimensions, which we've articulated in this paper. And so how many choices are there? 205 trillion is the number we came up with. So that's the design space of instruction. It's huge. If we want to get to the jet airplane of effective instruction, there's a lot of work to be done. It's not going to be purely empirical. We need some theory to help prune this space and guide us there. And part of what we did in this paper was suggest some recommendations for getting there, both by leveraging large-scale experimentation online, but also theoretically by building a better sense for how these different forms of instruction function to enhance different kinds of learning. I want to give you some examples now, sort of this data-driven process I mentioned, and how we've been going about that. We have done a number of studies using data to do various things, and one of those is to do a predictive assessment by using online interactions to predict end-of-course tests. For example, state tests. This is data from the Massachusetts 8th grade math test. And online interactions in an online system called the assessments. We're able to predict from those online interactions very accurately how students will do on the test. And those prediction models not only look at student performance, but they also look at how dynamically how much help they're needed. And we get metrics of essentially work ethic embedded in these models that are predictive above and beyond how well a student's doing as to how well they'll do on these tests. We've had other work that's used the log data from these system interactions to detect various emotions or disengagement gaming the system. And this is a screen from an intervention, Scooter the Tutor, who gets increasingly looks a little frustrated with you if you're looking like you're not engaged in the system, as one indirect form of intervention. There's also this help-seeking tutor that was built getting at helping students acquire learning skills, and again, driven by data. Another thing we've done with the data is run competitions. We did the 2010 Knowledge and Discovery Data Mining, or KDD Cup. Here we challenged folks to build better models of how students learn, and it was a real effort to try to engage the machine learning research community in understanding educational data. It was structured similarly, if you're familiar with the Netflix prize. Instead of having movie watchers making ratings of movies, we had students here solving. These are observations of their performance on steps in these tutors over time. And the data here is not their movie rating, but 1 if they got it right on the first try without any help, and 0 otherwise. Either they got it wrong or they asked for help. And in the competition, there was a held out section of this data, the end of every unit in essence, and the competitors had to build models based on the data they were given, submitted to the website to predict the held out data. There were 130 participants, a lot of predictions, and the accuracy greatly improved. There was a 15% reduction in error over the span of the competition, in essence. Actually, there were models that were even worse than this, but realistic attempts started about there. It's actually a kind of interesting question. What we learned here, I think these better predictive models kind of have a sort of black box character to them. And so that was one of the sort of frustrating things about this. But one thing we definitely learned is that there is some signal in this data, and there's some things to be discovered. One of the things that makes this possible in a rich way, and I think is really important to reflect upon as we're seeing more and more online activities in which we're getting data on students' problem solving, is the difference between what's mostly out there in MOOCs and Khan Academy these days, which is you get a question, it may be reasonably complex, you might sit down and do some work on paper, and 10 or 15 minutes later, you enter a solution online. Maybe it's 2 minutes later. Here, there's actually 2 different parts that are entered. In these intelligent tutoring systems and other kinds of more graphical user interface, more scaffolded environments. Here's an intelligent tutor Kurt Van Lane built for physics. They really try to unpack the problem-solving process, so it's not just the answer, but the work students do towards the answer. So the green stuff here is elements of the force body diagram that students are drawing and getting, in this case, positive feedback, because the green indicating that they got it right. They're entering definitions of variables up here, and here they'd be writing down multiple equations that describe the situation and accumulate towards a final answer. Here, they've gotten that equation wrong. So essentially the same kind of problem, but instead of 2 data points, we have 20 data points. And so that means much better sense of what students are doing and learning, but also pedagogically more powerful. So let me illustrate how that works. Here's one of the domains. We did some analysis in geometry. We were particularly interested in students' ability to not just bring formulas to bear to solve problems, but to do that in more novel situations where they have to combine formulas to say, find what's left over when you take that circle and cut it out of the square there. When we get data like this, every one of these steps is recorded in the data set, and we can look at the error rate across students, the average error rate over time, to produce learning curves. And so a learning curve looks like this, where on the x-axis we have opportunities to practice a particular skill and the error rate. And the trick here is the insight is that we can use this kind of data to identify what the skills are. So if we think that geometry is a kind of skill you acquire, and every time you practice a geometry problem, you get better at it, we can categorize that data that way, and we can create a graph and say, does that look like learning is happening? Is the error rate going down? And this is one of the visualizations that's in DataShop. This is a case where the knowledge component model is suggesting that there's just one component that you're acquiring. Yeah?
Real quick question. How's the x-axis ordered?
This is temporally the student's experience to work through problems like that. What order did they do each step in each problem?
So it's not like semantically versus like, it's literally just in order of like the opportunity that they were exposed to.
Yeah, well, if we take this same data and we label it more finely, so we make a distinction between what we think the skills are. So now that we have 12 categories, we're going to renumber that to say what's the first opportunity you had for circle area. And what used to be 2 in that graph might be the first opportunity to use circle diameter, right? And then we can regroup and re-average. And when we do that, same data reorganized, we now see a declining error rate. So this is empirical evidence that there are components of knowledge that drive learning. Up there, we don't see any evidence of transfer if we think the component's this one big geometry muscle that's getting stronger. Here, when we look at these finer grained components, we do. And what's particularly powerful about this technique is that it continues to apply. This is a hypothesis about what the skills are, and in the aggregate, it does reasonably well. But we can look at each one of these individual skills and ask, is the curve going down? So when we do that, we see some curves that are sort of reasonable. We also see some things like this one, which suggests that, hey, this is starting off pretty easy, staying pretty easy, and we're wasting students' time. That's a quick win to improve the system by reducing that. More interestingly, though, we sometimes see curves that look like that original one, where the error rate's not going down, it's staying high. And that could mean that they're not learning, but it could mean like that first curve in which we know they're learning, right? It just wasn't showing up because we had the model of knowledge wrong, that those labels are off. So we can dig in, and we can say, well, that composed by addition, what was it labeling? It was labeling these steps and these problems. And if we look at the error rate, it's high up there, it's pretty low for the next 2, and it's intermediate here. And here you have to switch on your cognitive psychology, math ed head and think hard about what's really going on to try to do this, to understand substantively what's happening. After doing that, we concluded that, tentatively at least, that the first step there requires that I really engage in planning to figure out how I'm going to combine the 2 areas. Once I've got the plan, all I need to do with new input is repeat the arithmetic. I just have to do the subtraction. In this problem, it's different because it's actually scaffolding, computing the needed intermediate subgoals. So the planning is in part being done by the scaffolding in the system, and that makes it slightly easier. So now we take that data, I'll skip past this next graph, and here's the 20 different steps across the different problems that were labeled with this and the range of error rates. We relabel it so that we get 3 different skills instead of the 1 represented in blue. And you're seeing the average here doesn't do a great job. We've got 3 different skills. It's not perfect, but it's much better fit to the data. More precisely, we can use a logistic regression model. This is a generalization of item response theory to build predictive models that we can get quantitative tests of how well changes in the model fit the data. The changes are reflected in changing this Q matrix that maps each step to the skills involved. The middle component's representing difficulty, the last component's representing learning and transfer over time. And that's what's producing these, the predictions shown in the green and blue lines here. So in DataShot, you can re-enter these models, and as you do so, you get updated prediction fit statistics like AIC and BIC and root mean squared error on various kinds of cross-validation. And what we often find is that the improvement, the reduction in error isn't necessarily that big. But as a matter of fact, we didn't change these models very much. 10 components went to 12 by changing 1 out of these, keeping the other 9 the same to 3 here. And so most of these models are similar. So unlike the KDD cup, we saw a large difference, but we didn't know what it meant. Here we have a small difference, but it's very highly meaningful. We understand, we can interpret it, and we can use it to make action. Yeah?
Really small question. Who's this particular interface meant for? Is it people who are trained in cognitive psychology / math ed, or is it?
Well, I would say ideally we want course developers to be learning engineers who know some cognitive psychology. They may know the domain, or they may work with subject matter experts to use this data to redesign courses.
My high school teacher will probably not know AIC and BIC scores.
Yeah. Right. But no, I'm thinking more of the course developer,
Okay,
right? Like a Pearson or a Coursera, or well, it's actually not Coursera because they're the platform developer. But yeah, actually, that's an interesting case because at the college level, it's usually the instructor, and so we either need to get cognitive psychologists working with instructors, or get more instructors doing discipline-based education research and learning some cognitive psychology. Here's how we take an insight like this and redesign a tutor. We're going to add new skills to this skillometer that'll change the way the pacing goes and better isolate the practice that's needed. We'll sequence differently. And what was most powerful actually in this study is we designed new tasks that got at this hidden planning skill we hadn't well enough identified. And this isn't sophisticated intelligent tutoring in this case. This is the psychology guiding us towards a multiple choice question, actually, but one that gets at the essential need here, which is to learn how to plan better. So you're just picking which of these is the best plan to solve that problem. And so we ran one of these in vivo studies embedded in a school, pre-test, post-test, looked at time to mastery. And the first big result is that time to mastery is dramatically reduced in the treatment condition. At the same time, we actually increased the time they spent on test steps where they were actually engaged in this critical planning skill. The consequence at the post-test was that when we look at items involving that planning skill, they do significantly better. Despite spending much less time on the individual area steps, they're not doing substantially worse there, although there is some suggestion that we maybe overdid it in reducing this, and there's some subtle reasons for that we're going to follow up on. So yeah, I realize that I'm running low on time here, but we've been pretty interactive along the way. I did want to do one more thing, which is to give you a sense for how we can, so this involved a heavy amount of cognitive psychology expertise to do this interpretation. Can we build a theory that can produce some of these features automatically? And the strategy's there been to create, actually I'm going to skip over, this next section is about a search mechanism that searches through these spaces of factors that people can propose, and it actually involves a sort of minor version of crowdsourcing. But I wanted to talk about is, can these cognitive models be automatically generated? And it goes back to this earlier slide here where we have this sim student theory that's been implemented in a computational model. It actually has 4 learning mechanisms. 3 of them are about learning production rules. The how is the then part. Where to look and when to do are part of the if part. And a 4th mechanism for learning representations. This is the grammar thing I referred to before. There's a key application here is the potential that we could build cognitive models and intelligent tutors essentially by teaching the computer how to do the task, and then we'd have the model and the tutor would come from that. So this representation learning part is the newest and most novel part of the, maybe the most powerful part of it. And it goes back to this chunking idea I mentioned earlier. And we've used probabilistic context-free grammar induction to learn the structure of domains by patterns of co-occurrence frequency to build these chunks. So it's an unsupervised learning mechanism that, just like the chess master who's seeing lots of boards, is going to learn chunks because certain patterns frequently co-occur. And you can represent those patterns in a grammar. we have actually a two-dimensional version of a grammar. We haven't tried it with chess, but there's some potential it would work there as well. So SimStudent, it works by being tutored. You build some kind of graphical user interface for your domain. You can enter problems into that. You say, this is the start state. Now try to solve it. And at first, SimStudent says, I'm stuck. I don't know what to do. Show me what to do. So in the interface, you demonstrate what to do. You give it a little clue, like labeling the skills that repeat. It gives it a better chance to collect positive examples. It does its whatever version of parsing it's learned so far. It learns a production rule. The next step, it says, I don't know what to do. Show me. It'll infer another production rule. We give it a little clue with labeling that. And again, when these labels repeat, that's when we collect together positive examples. So the interesting thing is when you go to the next problem, what can SimStudent do? It's inducing from examples here, so it may or may not get it right. So notice what it does here. This is a slightly different problem. It's a less sophisticated grammar. It doesn't know about the minus going with the 3, so it said divide by 3, and the author says, no, that's wrong. That becomes a negative example. The production rule will modify its if part to learn more. So we now show it what it should have done, and it'll adapt and go from there. So we've used this in 4 domains here, and we've compared the model that it came up with the model that was generated by humans. Most of the time, it produces more distinctions than the human modelers did. And most of the time, the consequence is that the prediction is more accurate. In one of these domains, it missed some features that the human modelers got right, and the prediction wasn't as good. It turns out some of those 6 are not represented here, and if you combine the 2, you get more than either before. Again, you can interpret this because you can look at the rules, right? And so it was a pretty interesting insight that came out of this that I hadn't really fully recognized before. Which do you think is the hardest of these 4 problems? The last one? Third one? Why the third one? Who said the third one? Why?
Because it's just a sign. I mean, I would understand dividing by a negative number or by a number, but I wouldn't necessarily understand dividing by a sign.
There's no number there, right? It's grammatically different in a subtle way. If you actually write the grammar, you have to write a different grammatical structure. SimStudent learns a different rule for that one than for the other 3.
Because that's the sign, the number, the variable.
And the last one was my intended foil. Actually, there's a little bit of subtlety here. If you call dividing by 4 a reasonable, if not ideal thing to do, that's actually what the tutor is doing. So, but yeah, it's actually quite a big difference, and it's a consistent one. And that's one that this machine system now discovered, and we can verify that it better predicts the data in the way I was illustrating before. Yeah.
This is something that pops up a lot in teaching algebra, is just on what side of the equal sign the x is. And so part of me is wondering, have you noticed any error rate in that?
Yeah, we've looked a little. I kind of thought that, but if it's there, it's pretty small. And it might be because this tutor pretty deliberately presents problems on both sides. But yeah. That is one of those subtleties that might matter, but that's the cool thing about the data. You have a hypothesis that it matters. You may or may not be right. Yeah, and it turns out it's actually an interesting question. If we trained students where the problems were x is always on the left, it would probably do poorly when it first encountered those on the right. So part of it goes to the variety of the experience. Just another illustration of tacit knowledge. And we could go into each of these 4 domains and give other examples like this of subtle insights. So it's not just about algebra, but it's about all domains have these subtle things that get students stuck, right? And we don't necessarily realize they're getting stuck because we're not quite consciously aware of it. Yeah, that's the bottom line message. You don't know what you know. Intuitive design is not reliable. We need data-driven learner models to do better. And that better is both in terms of improving the science, but also improving the practice of learning. There's tons of stuff we've done in addition to the cognitive, some of these motivational things and self-regulatory kinds of things. Actually building on some of Dan's work as well with inventing for future learning and some of these things, contrasting cases and so forth. Yeah, there's a lot of potential here. We think big data in education can really make a big difference. And I'd invite you to look into some of the opportunities we have. Actually, if you're interested in finding more about our summer schools or the Data Shop repository, I actually have some handouts about that. But thank you very much for your time and the conversation.